All right. So I think I've started recording. Cool. All right. Hello, everyone. This is week 3 of the software engineering interview prep course. And so today we'll be covering trees and linked lists. And I guess there's a reason why I put linked lists in parentheses. So this is the agenda. So we'll talk about linked lists, we'll talk about trees, and then we'll do two problems that are about binary trees, right? So that's kind of why I put linked lists in parentheses, and so let's talk about it, right? So why are we not doing in-depth class into linked lists? I think generally, right, so what I have here is that there are some pretty standard linked list tricks that maybe you've come across so far, maybe you haven't, but in general, I don't think they're not many of them, and they don't tend to be that complex. Once you see it the first time, usually it sticks. And oftentimes other linked list problems tend to get mapped into other categories, right? And so I guess the main takeaway is that a linked list is pretty similar to an array in that it's a linear data structure, and runtime and space complexity are also pretty similar to array problems. So that's like pretty much why we're not doing like in-depth problems into linked lists. But so this is like a little bit about linked lists, right? So the hare and tortoise technique is like probably like the trickiest one if you haven't seen it before. And that's just you keep one slow pointer and one fast pointer, and every iteration of your algorithm, you push the fast pointer ahead by 2, whereas you only push the slow pointer ahead by 1. And then other things to remember is like don't lose the head of your linked list, and sometimes you also need the previous node in your linked list, so keep that in mind. And then pretty much like any pure linked list problem, you just really have to stay organized with your bookkeeping and make sure that you're not getting tangled with your pointers. So just like stay organized when you're doing a linked list problem, and it generally turns out okay. And also I think overall, so these are like linked list practice problems, and what I was going to say is overall, like a linked list problem that you might see in an interview, I think is pretty similar to the CS201 level of a linked list problem. So I definitely recommend like going into the CS201 APTs and then just like doing a bunch if you feel pretty rusty on a linked list, but it's up to you. And then here are some more linked list problems. Some of these are pretty long, just as a warning. And then I guess this is also, this is like the top 15 most frequent linked list questions on LeetCode. The frequency thing is like a LeetCode premium for some reason. So you have that information now. I mean, I honestly, sorry.
You just clarified, frequency is by like the number of companies that ask the question, right?
I guess, I think it's all self-reporting. So like how much you trust the frequency is up to you. I wouldn't trust it with your heart, but yeah, just like I would say like maybe the like top 20 is like a pretty good range. But yeah, these are top 15 ones. I don't think you have to do all of them. I mean, just like do some if you feel like you want to do some linked list practice. I would definitely do reverse linked list. I think that's a good question. It also appears on the CS201 APTs. Cool. So next is trees. And I think this is like the general opinion about trees and tree problems is that oftentimes it requires a lot more brain power and thinking and like whatever than the number of lines of code it ends up being, right? Like tree problems are notorious for being very short, but like can be very complex, right? So this is kind of like the definition of tree problems that I've like built over the years. But I think maybe in some ways we can kind of break that down a little bit, right? So let's kind of talk about trees. And I think the major takeaway from today is this first sentence. And if you don't learn anything else from today, like, I want you to keep this in mind, and that's find the recurrence which helps you solve the problem, not the recurrence that solves the problem. So it's kind of a strange sentence, but basically, oftentimes you can solve the problem that you're currently looking at by solving a slightly easier problem or a different problem that's easier to solve, right? And it ends up making the solution to the original problem a lot easier to handle, right? And oftentimes this is the case with recursive functions, even dynamic programming. And it's something that I've noticed a lot of students, like in office hours, like when I'm TAing, is sometimes they're just so fixed on the actual goal that they kind of fail to see what other paths might take them to that goal, right? So that's definitely the takeaway, and I would just keep this in mind, right, when you do any sort of problems. And then the next thing is this idea of global state. So global state is, like, I would say, probably the clutch tactic for doing trees, and you basically simplify a lot of code by using any sort of global state. So definitely use that as an option when you can and when it's reasonable to do so. And then the last thing is just pure knowledge based, which is know your pre, in, post, and level order traversals, right? This is something that I feel like these kind of traversals should be pretty, like, you should be able to do any of these on the spot, and knowing these pretty much gives you full control over any binary tree structure. So definitely recommend reviewing these if you're not familiar with them already. Actually, to kind of continue with this discussion on traversals, one thing that people often fail to connect is that trees are basically graphs. I mean, they literally are graphs. There's just in this case, there's like a special structure to them, right? In that they're binary, and sometimes they contain like some particular structure, but they're essentially graphs. So we have these ideas of depth first search and breadth first search, right? And these directly correspond to the traversals that I was talking about before, right? So whenever you do a DFS on a tree, it's one of pre, post, or in order. And then if you do breadth first search, it's going to be a level order traversal. And then the methods that you can use to do them are stacks and recursion. I definitely always recommend using recursion because it ends up simplifying the code and less lines, so it's pretty nice. And then for breadth first search, the only option you have is using a queue. And I guess I want to make a comment about the pre, post, and in order traversals here. And basically, when we define these, we only define them with respect to when we visit the current node, right? So there's no assumption about if we go down the left-hand side before the right-hand side or the right-hand side before the left-hand side, right? Those are both options to us, and we should take whichever one makes sense in the context of the problem, right? So basically, the idea here is that we can do like the reverse pre-order, reverse post-order, reverse in order, where we visit the right-hand side before the left-hand side. So just keep that in mind as well. But yeah, one thing to mention about the global state from before is that sometimes you might not be allowed to use global state in an interview. Maybe the interviewer says no to you, or maybe, you know, that's just the reality. And so instead, you can often stick this inside a like stick whatever you're making global into the function header, or creating another function call, you know, whatever gets you to it. Global state is just probably the easiest, like the shortest solution to your problem. But you do keep in mind about pass by reference and pass by value whenever you pass things as parameters. Yeah. All right, and then yeah, so that's pretty much it about like the context of trees. If anyone has any questions about trees, now would be the time. Or linked lists. I kind of brushed over that quickly. All right, yeah, feel free to just drop it in the chat as well. Cool. So the first problem is binary tree maximum path sum. So first we have to define what a path is. So a path is a sequence of nodes from some starting node to some node in the tree. And the goal is to find the maximum path sum. And it does not need to contain the root. Okay. So traditionally, I've been trying to kind of keep this up over each class. Is whenever we look at a problem, I'll like give you guys the opportunity to ask any clarifying questions you might have. So if anyone has clarifying questions, please ask. I've also intentionally set the problem up so that there are some very valid clarifying questions that you can ask. Yeah, go for it. I'll give everyone like 30 seconds to read the problem. Yeah, we've got a question in the chat. Can a path consist of one node? It can consist of one node. That's a very good question. And note that, yeah, it's not actually clear from this definition. In fact, it's a pretty poor definition of what a path might be. So that's a great question. Yep, and then another question is, can the values in the nodes be negative? And the answer is yes, they can. Yep, that's also a very good question. I think the algorithm might change if they weren't negative, but maybe not. Cool. And yeah, I've also created a slide for some possible clarification questions you might have. So yeah, nodes can have negative values. We're not allowed to visit a node multiple times in a path, and yeah, path must have at least one node. And then the final thing is maybe just an edge case question. If the tree is empty, return 0. Yeah. So let's first look at an example of what this looks like. So here we have a tree of 5 nodes, and the question is, what is the maximum path sum? And so here, this is pretty easy to see, but it's going to be 15, 20, then 7, right? So whatever that ends up being. And note that it's not optimal to include 9 and 10 and negative 10 here, right? Because if we include these 2 nodes, then we're strictly decreasing the value of our path by 1, right? So we would never want to include this into any sort of maximum path sum, right? So that's just kind of a note. And so I guess when I was doing this problem, when I read the sentence does not need to contain the root, I was pretty shocked. And this was kind of my reaction. And I was like, oh, it's over. This problem is just way too hard. But I ended up thinking about it a little bit more, and this is kind of an interesting question of does it not need to contain the root? And so we'll kind of like digress here a little bit, and we'll solve this alternative problem, which is what about the max path sum, which must contain the root, right? Like if it has to contain the root, the question just got like significantly easier, right? We've literally like both objectively and subjectively it got easier. So I mean, I think we should be pretty confident about potentially solving a problem like this. Does anyone have any ideas, like however well thought out it is or not, about how we might want to solve a problem that like the max path sum which must contain the root? Any takers? Or even just maybe like some observation that you have about this that might help us move towards a solution.
I think you could like look at your maximum path sum on the left and then on the right, and then you add yourself to the maximum of either the left, the right, or the sum of both, or nothing.
Yeah, I think that's pretty much the idea. Yeah, that's pretty much exactly it, right? So I think the first thing to note is that, you know, if it contains a root, it either ends at the root or it goes through the root, right? So if it goes through the root, then that means the path is contains some nodes from the left-hand side and some nodes from the right-hand side, right? If it ends at the root, then it only contains nodes from either the left-hand or the right-hand side, right? So exactly what Kathy was saying, we kind of need to make this distinction, right? And then, so basically, we can recursively compute the max path, which ends at a current node. And this is kind of going to be the recursive part of this question. And then the last step is, yeah, exactly what Kathy was saying, right? We need to determine which combination leads to the best path, the best maximal path, right? Which goes to the root node. So this is, yeah, so I think if it has to go through the root node, the problem becomes a lot easier. And we can kind of write some code for this also. So we'll just write some code. I think there might be some like edge cases or bugs that I'm missing here, but anyways. So yeah, so this is our main function, max path sum with root. And we just compute the left and the right. And then here we take, is it either the left plus the root or the right plus the root? And then at the very end, we either return left plus root plus right, or the max end at root, right? And so now what is the recursive function? So we definitely need our base case, right? And here we compute the recursion on the left and the right. And then we either append the current node to the left-hand side or the right-hand side, right? Depending on which one is better. Can someone tell me why I'm taking the max between the recursion and 0? Like every time I call the recursive function, why would I take the max between this and 0?
Oh, is it because like you had in the first example, if that path is negative, then you just want to ignore it?
Exactly, right? Yeah, that's exactly it, right? If a path ends up having a negative value, we should never include it, right? I think another option you can do is instead of doing this, you can return the max between this part and 0. I guess it's up to you which one you want to do. But yeah, that's exactly it, right? We are avoiding negative values, right? And does anyone want to offer a runtime / space analysis on this problem? Luckily for us, tree problems generally are like have the same runtime and space complexity. So that's nice. Gotcha. So we have a potential log n here. So yeah, so if we let n to be the number of nodes, then yeah, so I think this will take a little bit longer than log n, right? So if n is the number of nodes, we have to we still have to visit each node once, right? So maybe does the chat want to try again on that one? And log n. Yeah, so maybe there's some fixation on log n here. So actually, it's just going to be n for the runtime since yeah. So we visit each node once, and then every time we visit a node, we just do some constant time operations, and then call it a day and leave the node, right? So it's going to be O of n for the runtime, and then I think the space complexity is sometimes a little bit tricky with trees, but does anyone want to talk about the space complexity? All right, we're getting an n squared here. So maybe do you kind of want to explain why, where the n squared is coming from? That's an interesting comment. Or if it was just a guess, that's also fine. Like a gut guess. Yeah, that's fair. So the response was it was just a guess because there was recursion. That's very valid, I think. It's a very valid reason. So usually with these types of recursion problems, we're really counting the number of recursive calls we have in a given stack, right? So if you've taken 250, maybe this is a little bit more familiar with how recursive calls, or maybe just function calls in general, use up memory. So we really want like the deepest point, right? So how many recursive functions get stacked onto each other? And so the cop-out answer is it's the height of the tree, whatever that is. The more stringent answer is O of n, because the tree could be entirely lopsided onto one side. In that case, we would have n recursive calls that stack on top of each other, right? So I think generally, unless you're doing something pretty fancy here, O of n is kind of your go-to runtime for just kind of iterating over a binary tree, right? So this is a max path sum with the root node, okay? So let's kind of revisit max path sum in general, right? So here's the max path sum is 15, 20, and 7. And now we're going to make like kind of a 500 IQ play, right? Where we just cover 10 and negative 9, right? So we've like deleted those nodes, and suddenly max path sum with root node solves this problem, right? It gives the correct answer for this, right? It fails here, but that's okay. It succeeds here, right? So now I'm kind of claiming that the problem that we had just solved is actually pretty similar, if not exact, almost exact to max path sum without the root node. So does anyone want to kind of offer an idea why? And we can go back to the code as well. Yeah, we can do kind of the brute force way, which is literally call max path sum with root on every single node. And that's very valid. Maybe I guess that's kind of what the image was pushing you towards, but let's try to be a little bit more fancy in the recursive function and maybe use some of the things that we touched upon earlier when we were talking about tree strategy. Right, I think the point that I'm making here is that any sort of max path sum has to go through the root of some subtree, right? So in this case, it passes through 20, right? And I guess we can also point out that the max path sum with root and the recursive function are actually pretty similar, right? We kind of have a very similar code. At least the first lines of max path sum with root are the same as this recursive function.
Wait, in the part where you're like calculating the maximums, everything, could you just look at like either the left without the root, the right without the root, the left and the right with the root, just the root? I think that'd be all.
Yeah, so you've definitely, yeah, I think you've broken down all the possible options, right? So one thing we can do to simplify that is, so at each recursive step, we'll just consider all the paths all like the potential maximum paths that go through the current node, right? So just like we were doing here, it either ends at the root, or I guess it ends at the current node, or it goes through the current node, right? And so then if we're kind of doing all of this business, then we need to, yeah, so the whole thing here is that, okay, we need to kind of keep an eye on the max path sum we've seen so far, right? And then this is kind of what I was saying before, is at each recursive step, we determine if we've found a larger path sum than the one that we're currently looking at. In that case, we update max path sum, right? And then at the very end, we can just return the max path sum, right? So basically, we're pretty much just moving some code around. And so we're keeping this global variable, and let's ignore the actual function call for now, and let's look at the recursive function, right? So here we're doing the same thing that we were doing before, right? These three lines are the same. And then here we are updating the max, right? So we're either keeping it the same, or we're saying, okay, it's the best of left plus right plus no.val, right? So maybe does anyone want to like kind of argue this point? Why would we add left, right, and the current value of the node here? Like it seems like we're failing to consider, oh, what if it's the left-hand side and the node, or just the right-hand side and the node, right? It's almost like this includes like the whole thing, right? Left through the current node into the right.
Is it because you already compared the left and rights with 0? So if it was negative, you already replaced it with 0?
Yeah, exactly, right? Yeah, that's exactly it, right? So we've already done this comparison. And so if the best path from the left-hand side is no good, then it's just 0. It becomes 0. And it's the same thing with the right. So we can make this kind of, I don't want to call it greedy, but kind of this cheeky like optimization trick, right? Because we've kind of ensured that the values are going to be at least non-detrimental to the current max, right? And then here's basically probably the most important line, right? Is that we're returning the current node plus the best from the left and the right, right? So either the path ends, like the path comes from the left-hand side and ends at the current node, or it comes from the right-hand side and ends at the current node, right? And then when we return that, then we can reuse that in here, right? So that's kind of the goal. And I mean, if you're at last week's discussion on DP, then maybe this kind of feeling, this like recursive feeling is familiar, in which case that's good. And I guess let's visit kind of the final function here. So we actually might not need this. Okay, I think there are a few ways you can do like this initial setup. This is just the one I chose. And we just call a recursion on the root, and then we return the max, right? And the reason we can do this is at each step, we're always updating the max if we can. And then, so by the end of it, our max is going to be what we want it to be, right? So any questions before we kind of try the runtime and space here? Yeah, so I guess we won't do like a whole discussion on it since it's exactly the same as the problem we saw before. But the runtime and space are going to be O of n here, where n is the number of nodes, right? I guess the whole reason why I showed this particular problem is because it really illustrates the idea that we solved a problem that makes it easier to solve our original problem, right? So without the root node, the problem looks extremely difficult. But then suddenly when we add the root node in, the problem becomes more manageable. And then it turns out we can use that intuition to solve our current problem, right? And if you kind of compare the two code solutions, I think maybe it'll be more clear how similar they are. Cool. So with that, we'll go into the problem 2, which is binary tree right side view. So given a binary tree, return the values of the rightmost node in each level ordered from top to bottom. So actually, the first time I saw this question, and when I was preparing this presentation and I saw this question, I was like, oh, this question is so hard. And then I kind of like relearned what I was teaching in this course, and then maybe I reevaluated my opinion. But I guess does anyone have any questions about the problem statement here? Yeah, I think this one's pretty self-explanatory. So it's literally going to be the rightmost node. So it might not be, they might not all be in the right half of the tree. But we'll see an example that might help. Yeah, I guess in this case it'll be a list. Yeah, that's a good question. What is the return type? Yeah, we'll return a list here. Yeah, so let's look into the example. Maybe that'll be a little bit more self-explanatory, right? So I've edited the previous tree, so that's more interesting. And the right side view is going to be -10, 20, and 7, right? So this problem is actually the fact that like the 7 is here when it's not on like the right hand side is pretty tricky. But luckily for us, we've reviewed our binary tree traversals. And so anyone want to have a swing at what might be the relevant traversal here? Gotcha. So someone's offering the post traversal. Yeah, so actually, I think maybe, so I think that the initial answer that I was hoping was the level order traversal. So if we traverse by each level, then I guess let's look at the example again, right? So if we traverse by each level, then the answer is just the last node in each level, right? So the level order is going to be maybe the first one that people think of. When I had originally solved this problem for the first time, I actually did not do a level order traversal. Maybe similar to what some of you guys are thinking. So let's just kind of go over like what the level order traversal solution might look like, right? So it's do a level order traversal, and anytime you finish a level, append the last value to some list, and then that's it, right? So yeah, I guess this kind of is stressing the point that we should be familiar with all of our types of tree traversals, since that gives us the most flexibility, right? So we'll kind of go over the code for this pretty much right away. So yeah, this is just some like edge case, and then we initialize a couple of queues. Yeah, so whenever we do level order traversal, we always want either 2 queues or a queue with some intermediate value that tells us that we're transitioning between levels, right? So if you haven't seen a level order traversal before, this might be a little bit new. But yeah, so we just keep 2 queues, and yeah, so we add the root to the next level queue, because at the very beginning we shove everything from the next level into the current level, and so every time the loop starts, the current level is always empty, right? Because of this while loop, right? So yeah, we shove all the next level nodes into the current level, and then we remove a node from the current level, and then if it's not null, or I guess if the left is not null and then the right is not null, then we add them, right? And then after this loop finishes, we'll have this node will point to the last node in the level order traversal, right? And then we can just add it to the right side array list that we have, and then just return that. So this problem is fairly simple if we're like pretty comfortable with level order traversal. I guess before we continue, we should do runtime and space. So space complexity is interesting, but runtime should feel pretty similar to what we've been doing. Take a second to think about that and offer your answer. Yeah, any ideas on the runtime? Yeah, so it might seem more complicated since we have the queues here, but I think the takeaway is that a node will go into the next level queue, then leave the next level queue, and go into the current level queue, and then leave the current level queue, right? So that is a constant number of operations to a single node, and we enter them. So the runtime will be O of n, right? And then the space complexity is maybe a little bit more interesting here. Does anyone want to? There's no recursion here, so there's no like stack usage. What the space complexity might be? Oh, number of levels. That's a pretty good guess, I think. Yeah, so the number of levels. I guess in this case, the while loop runs number of level times. But so instead of the number of levels, which would be the height of the tree, the space complexity is actually going to be like the width of the tree, right? Since each queue will contain all the nodes in a given level, the largest level, right, or the size of the largest layer would be the space complexity. And that is bounded by like n over 2 nodes. So I guess you could equivalently say O of n for the space, or like O of some other variable where that variable is the size of the largest layer. So why do you need to check if the current level is empty? So that's in the while loop guard, or after? Yeah, that's a pretty good point. Yeah, it should not be. And we don't need this check. I think we don't need this check. Yeah, because after the while loop terminates, the current level should be empty. Actually, Yeah. Yeah, I think that's true. We don't need the if statement. Good catch. Yeah, if you have any questions on the code, please feel free to roast my code. Cool. But I think the more interesting problem here is what about a recursive solution? And the whole point here is to kind of stretch our binary tree muscles and recursion muscles, right? So let's kind of go back, right? So we've got pre, post, and in order, right? And so now there are actually a few ways to solve this problem. So so a hint is that I think two of the three orders guarantees you to be able to solve the problem. I'm not sure about the last one. So you have a 2 out of 3 chance of guessing right what order we might want to try. Yeah, post order is one of the options. Today I'm actually going to look at the pre-order. So yeah, post and pre-order are pretty much the two options that we've got. I'm not sure if in order works. I haven't really thought about it that much. So maybe it does, maybe it doesn't. And yeah, so I guess the big thing here is that we're going to always want to visit the right-hand side before the left-hand side. So regardless if we do pre or post, we should always visit the right-hand side first, right? So, oh yeah, I forgot to animate that line. So the first thing to do is construct a right side view list, right? And then we do visit self, right, then left. And then now the big question is, what do we do whenever we visit a vertex? So maybe we can kind of like discuss this problem more in depth. Does anyone have any ideas of what we might want to consider whenever we're visiting a node? Or maybe even just when we're visiting the root node, what would we do? Right. So maybe we can think about this for a little. Let's just look at the love. What is this? This is the reverse pre-order. Right. So let's just kind of do the run on this. Right. So we start with a root, and then we do whatever we're going to do at the root, and then we leave the root and we go to the right first, and we do whatever we're going to do at this node, and then it has no children, so we terminate there, and then we go over here to the left-hand side. We do whatever we're going to do here, and then we leave this node, we go to the right-hand side first, do whatever we're going to do, and then we leave, and we go back to the left-hand side because 7 has no more children, right? So I think there are a couple things we need to keep track of while we're doing the recursion. Does anyone want to have a guess on what that might be? Right, I guess it's kind of going back to the whole point of the problem. Yeah, so I guess in this case, the thing that we really want to focus on is the level, right? If we had information about like what level each node was at, this problem would be easier to solve, right? So with the preorder traversal biasing to the right-hand side, we always visit the rightmost node possible, right? In any given layer, right? Um, as we saw with this like run through, right? So now the question is, right, how do we know when to add like a particular node to the list that we're building? And maybe to make it easier, right, is like what about the list is true when we're at the root? Yeah, so when we're at the root, the list is going to be empty, right? Since the root is the first node we visit, and then we add it, right? And I guess so. Just keeping to this example, right? So when we're at the root, we add it to an empty list. Then when we move to the right, we're going to add this node, and when we do add this node, it's going to be when the list has size 1, right? So the whole thing with this particular ordering is that we always visit the rightmost node in any layer first, right, before all the other nodes in the layer. So basically, when the level agrees with the size of the list, then that means we know that we're at the right node and we can add it in, right? So there's like all this thought behind this recursive solution for a fairly short number of lines of code, right? So we have a global list, right? And then let's just look at the main function first. So this is the base case, and then we return an empty list if the root is null, and then we recurse. And here we're passing in the root node and also this integer, which is a level or int, I guess. And we have this if statement: if the level of the right, if the level is the same as the size of the list, then that means that this node, right, is the rightmost node of the level that we are working on right now, right? So we add it to the list, right? And then we actually don't need a base case here because we have these two if statements checking the nullity of the children, right? So if the right is null, then we recurse on the right-hand side first. We increment the level. If the left is not null, then we recurse on the left-hand side and increment the level, right? And basically, the good part about this level parameter is that we always pass by value. So level +1 is whatever happens to this guy like has no effect on this level, right? So hopefully this is kind of like an interesting take on maybe a simpler problem. There's also so this is a pre-order traversal. I think there's actually, you could do post order. You might actually be able to do it in order as well. I think post order might be, but yeah, I think you can do this problem like in multiple different ways, which I guess is the point. And the runtime and space complexity here is going to be the same, right? Linear in the number of nodes. So any questions about that solution? Maybe I rushed a little bit through some of the thought process. Cool. Yeah, so here are basically some tree problems that I recommend. So some of these problems are like serialize and deserialize and construct binary tree from pre and in order traversal. These like have less to do with the values of the tree and more to do with how good you are at like working with trees. So I definitely think these are both like pretty valuable problems to do. Diameter and LCA are fun problems for like recursion type. I think these are both recursive solutions. And then of course the CS201 APTs are in general like a super good resource for trees and linked list problems. So yeah, I guess that's pretty much it for today. So thanks for coming and participating, everyone.